Hello all. Coming to the sixth session of the chapter Stereochemistry, you will learn about assigning configuration to geometrical isomers by physical properties through melting point and boiling point determination, by dipole moment, by their pKa values as well as their solubility measurements. These are the various methods by which we can assign configuration to geometrical isomers. We know geometrical isomers are also a part of stereoisomers, but they are not optical isomers. What are they? They are isomers which will be arising due to restricted rotation about carbon-carbon double bond. Such compounds, such isomers are termed to be geometrical isomers. What are the properties of geometrical isomers? We know geometrical isomers are termed as cis isomer as well as trans isomer. In the cis isomer, similar groups are on the same side of the double bond and they are close together and there will be steric repulsion between the group. So, they will be unstable. Cis isomer will be comparatively unstable than trans isomer. In trans isomer, the groups are on the opposite side of a double bond. There is no steric repulsion and they are more stable. So when we compare the two different geometrical isomers, cis isomer and trans isomer, we can say trans isomer will be comparatively more stable than cis isomer. Now, how can we assign the configuration for geometrical isomer? Assign the configuration in the sense, how can we determine whether the isomer is cis isomer or trans isomer? We follow different methods for that. Geometrical isomers are not mirror images, so they are not enantiomers, but they are diastereomers. Geometric isomers have different physical and chemical properties. This property is used to assign configuration for geometrical isomers. They have different physical and chemical property, whereas optical isomers are having same physical and chemical property. So none of these methods are applicable to assign the configuration for optical isomers. Only for geometrical isomers to assign the configuration, these methods are applicable. We'll see what are the different methods by which we can assign the configuration for geometrical isomers. The different method what we follow are, one is physical property, then chemical property, then spectral properties, and also from the formation of cyclic derivative. What do we do in physical property? Physical properties of cis-trans isomers are different and this property is used to assign configuration like melting point, boiling point, etc. Melting point of trans isomer is higher compared to cis isomer due to symmetry of the molecule. Melting point of trans isomer is higher because it has a particular symmetry. You can see here, this is the trans butene dioic acid and this is cis butene dioic acid, or commonly we can say this is malic acid and this is fumaric acid. So malic acid is a cis form and fumaric acid is the trans form, which will be having more symmetry. Trans isomer, fumaric acid will be having more symmetry, so that will be having high melting point. Cis butene dioic acid is having only 135 degrees Celsius as the melting point, whereas trans butene dioic acid will be having the melting point 287 degrees Celsius. So whichever is having higher melting point, we can say that is the trans isomer. Now, based on boiling point, how can we see whether the isomer is a cis isomer or a trans isomer? Boiling point of cis isomer is always greater than that of the corresponding trans isomer because it is more polar. Please listen here very carefully. Melting point and boiling point, the effect are in the reverse order. In the case of melting point, trans isomer is having high melting point, whereas in the case of boiling point, cis isomer is having high boiling point. because cis isomer is more polar, whereas trans isomer, the polarity will be 0 because of the symmetry. The polarity of this CCl and this CCl will get cancelled. There will not be polarity. So when polarity is not there, boiling point also will come down. So the high value for polarity is therefore cis isomer, and so we can say whichever is having high boiling point, that is a cis isomer, and the other one is the trans isomer. Now, how dipole moment measurement can be useful in assigning configuration. Similar way, almost similar to the determination of polarity, the cis and trans isomers have different dipole moment, which is used to distinguish geometric isomers. The trans isomers are symmetrical and hence will have zero or low dipole moment as compared to cis. The same thing here, this is 1,2-dichloroethylene. This is cis form. It has got a value dipole moment mu equal to 1.85 dB. Whereas this trans isomer, you can here this CCl is towards this direction. Dipole moment will be towards this direction, whereas this CCl dipole moment will be in the opposite direction. Both will get cancelled and the dipole moment will be 0 dB. Now, how about the other cases also? The cis isomer will be having a particular dipole moment value, whereas the trans isomer will not be having any dipole moment value. So based on the dipole moment value also, we can make out whether it is a cis isomer or a trans isomer. Now, how can we use the pKa values for assigning the configuration as cis or trans? Maleic and fumaric acids are the dicarboxylic acid and having a pKa value. pKa is a dissociation constant value, pKa of that value. Acid strength are depending on configuration. The strength of the acid depends on the configuration. Maleic acid undergoes ionization to form maleate ion, which is stabilized by intermolecular hydrogen bonding due to proximity of the two carboxyl groups. Proton is more firmly held and second ionization is very difficult. Thus, maleic acid is stronger acid for the first ionization but a weaker for second ionization. You can see here, this is maleic acid. Maleic acid is converted to malate ion in the first ionization. Once it deprotonates, the O- and the OH group of the second carboxyl group will form the intramolecular hydrogen bonding. Because of that, the second ionization of this proton is very difficult. So second ionization is weak for maleic acid. In the case of fumaric acid ionizes to fumarate ion. Fumarate ion gives up a proton more easily. This shows that the two carboxyl groups in fumaric acid are far away, which cannot be stabilized by hydrogen bonding, and second ionization takes place easily because there is no hydrogen bonding. Hence, fumaric acid is stronger acid for second ionization than maleic acid. This is fumaric acid, C double bond C, COOH, COOH. As the both carboxyl group are on the trans position, opposite position, even if after first ionization, it cannot form hydrogen bond with the hydroxyl group of the second carboxyl group. So there is no intramolecular hydrogen bonding. So the deprotonation of the second proton from the carboxyl group will be very easy from fumarate ion. This value is indicated in this pKa value. We know that higher the pKa value, lower the acidity of the acid. Now, how the solubility measurement can be determined? For assigning the configuration, solubility of cis isomer is more. For example, solubility of maleic acid is 3 gram per 100 ml of water at 293 Kelvin, and solubility of fumaric acid is 0.7 gram in 100 ml of water at 293 Kelvin. If you compare the same solvent, the same temperature, then we can say cis isomer solubility is more than the trans isomer. This is due to the reason that the molecule is cis isomer are less tightly held in crystal lattice. What may be the reason? More symmetry is for trans isomer. When the symmetry increases, the arrangement of the molecule in the crystal lattice also will be too symmetric and it will be very tightly held. As the cis isomer is having less symmetry, they will be less tightly held in the crystal lattice and that will affect the solubility of the isomer. So these are the different ways by which we can assign the configuration for geometrical isomers. We can use physical property, we can use melting point and boiling point measurement, and we can use dipole moment measurement and pKa value and also solubility measurement of these isomers to assign the configuration.